So let's get started on our first example. We're going to be solving y double prime minus xy equal to 0. This is going to be a really long one, so you could go ahead and think for now how you would solve that after other sections in class. But we're going to apply our new series solution. And so first I have to think about this format that we said our differential equation would be in. So there's nothing in front of my y double primes, that part's fine. I have that my function p of x is just 0, and my function q of x is minus x. So x0 equal to 0 is an ordinary point. I don't really have any problems. So I can go ahead and move forward. Radius of convergence, if I want to say it. Would be that sort of my x minus 0 less than infinity. I'm never going to run into issues with q or p because p is 0. So my radius is infinite. For my assumed solution, y equal to the infinite sum from n equals 0 to infinity, cn x to the n, I'm going to have y double prime is the sum from n equals 2 to infinity of cn times n minus 1 x to the n minus 2. We learned how to take that derivative before, and at this point we can just go ahead and plug it in whenever we need it. And what we need to happen is we need to have 0 equal to y double prime minus xy, which is the sum from n equals 2 to infinity times cn n minus 1 x to the n minus 2 minus x sum from n equals 0 to infinity cn x to the n. And I need to, what I need to do is manipulate the series so that I can solve for my cn values. So I've already done steps 1 through 5 at this point. I checked that everything was okay, I assumed this solution, and I plugged it in. So let's look at what we can do here. I'm going to leave the first series alone for now. And then I'm going to go ahead and pull this x inside. Sorry, I knocked my screen over. Pull this x inside of this series right here. So that's the sum from n equals 0 to infinity of cn x to the n plus 1. That's sort of x times x to the n. Oops. Just from pulling that x inside. And now what I want to think about is trying to get these two series to have the same bounds and the same powers x. So I think what I'm going to do first is I'm going to try to make the powers x match. If I remember how it went when we did that other practice problem, I know that if I make my indices match first, then I kind of have some like catching up to do sometimes with my powers x. And since these ones are kind of far apart, I know that my indices won't automatically match. So that's what gives me the intuition to start with bringing the x's to match. So I want to have x to the n right there, and I want to have x to the n right there. Oops, okay. So if I take x to the n minus 2 down to x to the n, what happened before was when I plugged in 2, I started at x to the 2 minus 2 is x to the 0. So if I want my first terms to match, and my first term is going to be x to the n, I'd better be starting from n equals 0. Now I can go ahead and change all of these things to match what I just did. I'm going to talk through how to change all the things. The other way you could think about it is I took n minus 2 to n, so I added 2 to n. So what's going to happen here is I'm just going to always be adding 2 to n. But we'll kind of show how that works. Okay, so I've got this Cn. Originally that started at C2. If I plug in 0 to start, I'm going to need to have C sub n plus 2 to get C2 to start. I think I'm going to run out of room here. Okay, originally I plugged in n, that gave me a 2, so same reasoning right here, that's going to become an n plus 2. Before, when I had n minus 1, that was 2 minus 1 is 1. When I plug in 0 to start, I guess I need n plus 1. That way 0 plus 1 is 1, and they match up. So that's how I do that sum. Move that over there, because I need this space. This one I'm going to use that second way of reasoning that I just told you about. So when I moved x to the n plus 1 to x to the n, if I take n plus 1 to n, that means what I'm doing is I'm taking away 1. So if I start with Cn, I just take away 1. That's a fair way of reasoning as well. And it works the exact same way as the other. Just whatever makes more sense for you, go ahead and do that thing. Okay, so now what we've got is powers of x are the same. I'm going to erase those reasonings too, because that makes everything really messy to look at. So powers of x are the same. Now what I need is for my indices to line up as well. All right, I started from n equals 0. X to the 0 plus 1 was 1. So now when I go to x to the n, I'd better move that to n equals 1. Cool. So here I was subtracting 1. You do the opposite when you change the indices. So I was adding 1 there. Now I need to make the indices line up. So I want to have 0 equal to sum from n equals 2 to infinity. No, n equals 0 to infinity of Cn plus 2, n plus 2, n plus 1. X to the n plus the sum from n equals 1 to infinity Cn minus 1 x to the n. So what's usually going to be easiest is for me to go up in indices, because all I have to do here is just peel off my 0 term. So my 0 term would be c sub 0 plus 2 is 2 times 0 plus 2 is 2 times 0 plus 1 is 1, x to the 0. And then just hold on to all my other terms. And the other sum is already where I need it to be, so I can go ahead and leave it the way it is. And now my powers line up and my indices line up, so I can combine everything. So I've got 2c2 is just simplifying that term right there, plus the sum from n equals 1 to infinity, Cn plus 2 times n plus 2 times n plus 1, plus Cn minus 1, all times x to the n. And I want that equal to 0. So what that's going to look like is making sure this is equal to 0 and this is equal to 0. But we're going to talk about that in the next video.